Hi Grade 10s, it's good to be with you. Welcome to Learn Extra for Science. My name is John and we're going to be taking a look at some important principles that are involved in doing this fantastic subject called physical sciences. So today's session is all about the tools you'll need to be a success in science. So let's have a look at the key concepts that you'll need to go and learn from. Today we're not just focusing on what's going to be in your exam, but trying to get you a little bit aware of what it is to be a scientist and to think like a scientist. So let's have a look at those tools of science as we're calling this session. Here we go. Things that I want you to be aware of and I want to discuss with you is, first of all, to ask the question, what makes science different? I know that you've got lots of other subjects that you will choose from, but what makes science different? What's different about science? Now, I know that some of you will be saying, well, it's experiments. Well, that's part of it. But let's have a look at that in just a little while. The second thing that we want to look at is, as we distinguish the differences that we get in science, we want to take a look at important skills. In other words, investigation skills. We're going to be talking about what are variables, what are values, and what is a fair test. In other words, what's the relationship between variables, and how can we come to some conclusions about the relationships between variables? Now, one of the other things that you're going to do as you go through grade 10, 11, and 12 science is that you're going to need to have some mathematical skills. Now, I'm just going to introduce some of the important math skills that you already know, but that you'll need to make sure that you improve on, you get really good at. Because unfortunately, one of the things that you're going to find is that when you do physical sciences, a lot of the exam work is based on your ability to solve problems using mathematical tools. Now, that doesn't mean that you can't do science if you're not good at maths. You can practice the science and become good at the maths because you need to be thinking like a scientist. So that's the very important thing that I want to remind you about. Your maths is going to be important, but there are some very important tools that you're going to need in science. And so I would like to start with asking you to think about what is different about science. And let's have a look at some of the things that I've listed. Well, when you think about a scientist and you think about some famous scientists, one of the things that I'm sure you'll recognize is that scientists always ask questions. And this is something that I would like to ask you to be aware of. When you're looking around and you're going from school to home or you're playing sport, I want you to start engaging with the real world and ask questions. Ask questions. Wow, why is that? I wonder why. What's happening there? Those are questions that are going to help you start engaging with what real science is. And that's what scientists have done through the ages. When you think about it, some of the famous scientists, some of them, as legend goes, like Newton, sat under a tree, saw an apple fall, and said, I wonder why the apple's falling. And what did he come up with? He came up with the idea that there must be a force that we now know is a gravitational force around the Earth. So we recognize that by observing, by asking questions and then thinking about them, we can come to some conclusions. Now, the second word or the second thing that I've put there is observations. And what are observations? Well, it's using our senses. It's what we can see, it's what we can hear, and in some cases it's what we can smell. When we're talking about chemistry, sometimes smell is an important factor as well. It's also what we can touch. So we use all our senses when we're making observations. And in making observations, we're able to begin to gather information. You've gathered a whole lot of information, and then you want to put it into some sort of order. So I'd like to just show you an example of that. If we were taking a look at some objects, and I've got some here, like this wooden rod and this piece of metal here that's a little silver colored or orange colored really. we have to ask the question, what's the difference between them? What properties does the wood have that the metal doesn't have? Well, or the other way around. Well, we know that the wood can bend a little bit, so can the metal, and we can bend it quite a lot without breaking. And if we try to do the same thing, put the same amount of force on the wood, we'd get to a point that perhaps the wood would start to break. And there you can see it, it's breaking, whereas the metal, if we pull it and pull it and pull it, we can bend it. So the metal has a particular property, apart from having a different color, it's a different strength too. It's able to bend. You're able to pull it back and put it back into shape as well. Now, not all things have the same properties. It's only by doing some investigation, some observations, looking at the properties of things, that we can come to some sort of way of grouping them together. The skill of grouping things together is known as classification. So what we would do when we classify objects, we'll say, well, these properties, particular properties that we've seen from observations, allow us to put things into two groups. We can get things that are metallic, and things that, even though they don't look the same, for example, this rod and this piece of aluminium ball that's just been crunched up, they're both metallic. They don't look any like each other. This one is a silvery color, this is an orange brownish color, but they're both metallic properties. They both have shiny surfaces, they're both good conductors of electricity, and we could carry on the list. They can both bend, they're both of different strength, and so we can make some conclusions about classifying them, both to see what the similarities and differences are. So scientists, whether they be botanists who group things together to classify plants, or zoologists who do the same thing for animals, or chemists who do that for materials and for elements, or physicists, they have ways of collecting and grouping data. One of these skills is called classification. So we will sometimes be asked to classify things. That means put them into groups of similar nature. And so that's one of the things that scientists do. But you know what? Other people do that as well. Librarians classify things. There's a whole library classification system, and researchers do it as well. So we mustn't think that all these skills are unique to scientists, but there are things that scientists do. Other things that you might not be aware of is that scientists do some reporting. Having done an investigation of some sort, having collected their observations, they're going to write them down. They can write them down in a journal format, and they can start to think about and describe the qualities of different things. So you might want to keep a journal of things at home and start to think about what the properties of materials are that you use every day. Which one of them are strong? Which of them are weak? Which of them have colors? Which of them are transparent? Which of them break easily, like the wood that we snapped? Which of them bend? All of these are properties. We could record them in a journal, say, this is what I noticed. These are the questions that I've been asking. These are the ideas that I've had. And at that point, we are investigating the qualities of different things. And we call that sort of investigation, or that sort of report, a qualitative. It's not talking about numbers or measurement. It's a qualitative approach. And a qualitative investigation leads us to think about some ideas deeply, so that once we've thought about them, we can come up with some I think questions. I think that from what I've observed, I have this idea that this may happen if I do something. We then need to start testing it. When we test it, we take measurements. And taking measurements means that we're dealing with numbers. So we're not dealing with qualities anymore, but we're dealing with quantities. So there's a second type of reporting or investigation that scientists do, and that's called a quantitative report or investigation. Now, we're going to go into some more details about this word investigations. Investigations are things that scientists conduct to try and answer questions. They could either be qualitative or quantitative, and you'll notice that there are different ways of setting these investigations out. We'll have more to say about particular things in investigations a little later. One of the things that comes out of quantitative investigations is that scientists often like to put things into graphs. And although this is a mathematical idea, scientists use graphs extensively. They've got different things that you can interpret about the relationships between factors that we can read off from graphs. Now, in terms of our investigations, what we often use is some terminology. One of the words that we use, which is kind of a big word, but you need to be aware of it, is this idea of a hypothesis. And a hypothesis is really what you expect. Before you do a test, what you expect. Usually, what you expect comes out of your qualitative observations, your qualitative investigations. You've had an idea, you kind of think about it, and you write down what you expect. Then you go through a testing process where you test and you make measurements, and you come up and see the idea that you thought would happen, is that really true? That's what science is all about. Taking your evidence and examining it, testing it, and trying to see if the conclusions that you make support what you originally thought. Sometimes you'll come to the conclusion, no, I had the completely wrong idea. That's not bad science, that's good science. You've come up with a new idea. And so science is growing all the time because people are having some crazy ideas. They've got different thinking. They've made different observations. They've made different discoveries. They're using different instruments to explore both space and in the very small aspects of a nanotechnology, which is very, very small, almost at an atomic level. Instruments that can give us feedback about what the world is made of to answer those really important questions. How did we get here? What's happening? Why are things happening the way they do? Now, all of these observations are collected together into what we recognize as a theory. And so people come up with, after they've done experiments, they come up with their ideas and they put them together and they write their observations together and they come up with what we say is a theory. Now, a theory tries to explain what's happening. We recognize that, for example, that from our observations, Newton recognized that the apple fell to the ground. He also recognized that the moon circled the Earth or orbited the Earth on a regular basis. And so he had to kind of come up with a way of explaining why this is happening. The way he explained it was to introduce the idea that there is a force called gravity. And that becomes a theory of gravitation. And so he then developed from his observations what he thought was the explanation for what he observed. He didn't fully explain it. He came up with some principles, theory that we need to test all the time. He also developed some laws, which he said, well, look, I found these things and they seem to work all the time. It gives a part of his observations. So he started to explain what he was observing through laws. And so that's what scientists have done. Things that are always seem to be the same, they're kind of explanations or summaries of your observations. So these can be summaries of observations. And these are explanations of your observations. So they're different. Theories and laws are different. Theories can change. Usually laws are fixed. There are not many laws that change over time. They're usually fixed. They're determined by experiment. Explanations of why things happen. Explanations of why. Those can change. People can have different ideas. And over time, people have changed their ideas of science. Think about the atom. The very idea of the word atom, small particle of matter, the smallest unit of simple matter. We'll have more to say about that later, but over time, the ideas of what makes up matter has changed from being solid particles to being all the same size and all the same mass to being a very different idea to what we have today. And so we're not going to go into those theories, but just to say that theories don't always stay the same. When new evidence comes up from experimentation, then what we find is that the theories need to change. Get new laws, bringing about new theories. So that's what makes science different. It does require imagination, it requires creativity, it requires problem solving. And often in today's world, scientists work together in teams. They share data, they compare results, they do the same sort of thing. They use the same experiments and they repeat them to make sure that things are accurate and they're precise. And those are very important words that we're going to explain, as I said, in a little while. So that's what makes science different. The core of science isn't about just reading books. It's not just about finding out what somebody said because it's put onto the internet. Science is much more involved in let's set up some experiments. So whenever you've got a theory and you're presented with a theory, we need to ask ourselves, well, what are the experimental results that help us explain this theory? Or give rise to this theory. And then the next thing that technology and engineering takes, it takes those theories and says, how can we use these to make our lives better? So science is a really important foundation. Without doing the investigations, without doing the research, we won't be able to apply our knowledge of what's happening, and we won't get these fantastic new discoveries that are part of engineering and technology. So let's just make sure that you're all on the right page, and let's make sure that we've got the ideas of what an investigation is all about. So I want to deal with seeing investigations of the core of science. I want to start by talking about some investigation skills. And so the first thing that I'm going to do is I'm going to put in front of you these shapes. And I'm going to say to you, take a few moments, have a look at those shapes, and think about them. What do you notice about them? How would you describe them? How are they different? How are they the same? What properties do each of those shapes have? And as you're looking at that, I want to introduce you to the idea of what is a variable. A variable is something that makes things different. And so I want to think about what are the variables when we look at these shapes. What are the variables represented here? I hope you've got some ideas. As you've looked at those shapes, well, what variables do you notice? Now, I've noticed that there are groups of shapes. One group of shapes has 4 sides. So we could think about the number of sides as being a variable. And the other thing that I've noticed is that you've got some things that are blue and some things that are a yellow-orange color. And so I would recognize that the 2 variables that I want to talk about here and mention is we've got a variable that is the number of sides and color as another. So if we think about these and we say, well, number of sides, we recognize this is a square, that's a square, and that's a square. They're all squares or rectangles. But this one is a triangle, right angle triangle, right angle triangle, right angle triangle. And what we recognize is they've got 3 sides, where these ones have got 4 sides. So the value for number of sides is either 3 for the triangles or 4 for the rectangles. These things. We'll recognize these are called rectangles, and these are called triangles. Now, the other thing is that if we just look at the rectangles, we'll notice that this one has a particular size, this one is slightly bigger, and this one is slightly bigger. So not only is it number of sides, but it's also another variable is size. So what would the values be? If the variables were number of sides, and we can say the values are 3 sides and 4 sides, what would the values for color be? You want to have another look at that? Let's just check. Have you got it? The color of these things and the color of these things. Well, I'm sure you've got that. You recognize there are 2 values for color. Blue is the one value for color, and I'm going to call it orange is the second value for color. But now what about size? Notice the rectangles and the triangles. The bottom side here is the same length. That bottom side is the same length. If I can pick it up, prove that to you. Recognize that one, same length. That one is the same length. And this one is the same length. So we could go and do this in a little bit more detail, but for the moment, just roughly, if we were to try and describe size, I think it would be enough to say that we've got small, medium, and large. So what you need to recognize, just looking at something simple like that, hopefully you can begin to see what the difference is between a variable, which is something that is different between objects. Variable, something that is different. The value describes that difference. So we've said enough about that, but just to make sure that you've got it clear, when we spoke about size and number of sides and the color, notice all of these were just quite easily observed. But we could go and measure those. We haven't. We could go and measure, and if we go and measure, we could take a ruler and measure the sides and the length and so on, and be able to describe the difference in size in terms of area. But that would require some calculation. So when we do measurement, what we need to recognize is then we're dealing with quantities. Quantities. These are qualities more. They're not really related to measurements. The other thing with measurement that we need to be aware of, when you measure, there are important units to remember. And we're going to have a little bit more to say a little later about the importance of units. But I just wanted to mention here that variables often, or values, often have units. We must make sure that we work with those units correctly. Okay? Now, that was a simple illustration of the difference between a variable and a value. And I hope you found that useful and that you will continue to remember that as we move on. But now, let's think about doing something a little different. I want you to think about, here's a question. Something that you might have seen and you might have wondered about as you've looked around you. It was one of those things that somebody long ago actually started to think about it. A man called Galileo Galilei. And Galileo, he's quite famous because he invented the telescope. He looked at the moon and the stars. He also did the very famous dropping of balls off the Leaning Tower of Pisa. But there was another experiment that he's also very famous for, and that was what we call a pendulum. And so I want to talk about a swinging pendulum, because a pendulum is something that you can make, and it's not difficult to make it. You can use some simple material, and it doesn't have to be too difficult to tie together. I've got some string here, some twine, and I'm just going to attach a mass piece to it, just this little lead weight that comes from a tire. Just tie that on, and here we've got a little bit of a pendulum. So what is a pendulum? You can hold it up like that, and you can swing it from side to side. Now let me just do that again so that you can have a more careful look. If I'm holding it, I want to just get it into place so that you can see it. Pendulum swings from side to side. Now, what you might want to ask yourself is, as you're watching the pendulum go, Well, what makes it go backwards and forwards? Well, it's the force of gravity, to answer to answer simply. But if I drop it from here, is it going to take longer or shorter than if I drop it from here? Now, there's an interesting question. What would happen if I changed the length of the pendulum? Instead of making it very long, I made it very short and swing it from the same distance. Let's just do that. Hopefully you can see that it's swinging a lot quicker. Now, what makes it different? What makes it swing? We could also try, and instead of using this weight, use a nut, something like this, that is a lot less mass. Will the mass influence the swinging pendulum? So having done some exploratory observations and ideas about the pendulum, it's time for us to have a look at what is a fair test. How can we investigate the swinging pendulum? And when we have a swinging pendulum, we need to have what is known as an investigative question. And I've come up with this idea, is what factors influence the time taken for a pendulum to swing. Okay, so what factors? What are the variables that we could change? So let's think about those variables. I've shown you some of them. Can you think about what they might be? Let's have a look. Well, I think the one thing that we've changed is the length of the string. The other thing that we could change is the mass of the bob. That's the thing that you're swinging, the mass of the bob. Or you could say, what about the height that you release it from? The height it's released. So here we've got three different variables. I'm going to say length is L, mass is M, and height can be H. So if we're wanting to make some relationship between those are the things that we can change. And what that's going to influence is the time. That's what we're wanting to find, the time, T. Now, what time? The time for the pendulum to swing from its maximum position through the rest position and back again. Now, that is one cycle. And if we want to give a fancy word to that, scientists call that the period of the pendulum. We're wanting to find out what factors will influence the period of the pendulum. All of them, maybe, but how are we going to test them? Now, here's the important thing that I want you to recognize. Even though we've identified all of these variables, length, mass, height, and we recognize the thing that they influence, what factors in the time, that's the outcome variable. That's the thing that we're interested in finding out about. What we give this is either the outcome or we call it the dependent variable. It depends on something else happening. It's the dependent variable. Okay? Think about it as the outcome or the output. So what have we got here? We've got three inputs. Now, if we're wanting to know which one of these really influences time, the period of the pendulum, then what we're going to need to do is to make sure we don't have conflicts between them. Because maybe mass is doing one thing and the length of the string is doing another. And maybe the height is influencing it in a different way. Well, maybe it's a case of that the longer the string, the longer the time. And if we change the mass and the length of the string, we won't know which one is actually producing the longer time. Is it the mass or is it the length of the string? So here's the thing. When you're testing variables, you must have only one thing that you change, one change that produces one outcome, one output, one change over here. This one change is known as the independent variable. So now you're asking me, but hold on, what about the other variables? Well, when we do a test, we must make sure that we control these other variables. If we're going to do an investigation and we're saying, I think that it's length that is influencing the time that it takes for the pendulum to swing, well, then we must make sure that the mass and the height are always kept the same. They mustn't change. They must be kept constant. Only then will it be a fair test. You can imagine it if you were wanting to do an athletics race and you wanted to see whether Joe and John were better runners. Who was the better runner? Well, you wouldn't give John a 50-meter head start and then time them over a different distance. That would not be a fair test. In the same way here in science, we must investigate, we must think, we must observe, we must identify the variables. And then we must select one variable and compare it to the output or the independent variable. It's the one we select, the one we control, and say, how does that influence the output? Change only one thing at a time. That's the important point. So, from our previous little experiment or little idea, what I'm going to suggest is a hypothesis. And here, I'm going to, having looked at those variables, remember the investigative question, what factor or factors? I still don't know what the factors are, but I'm going to break them apart. And I'm going to do an investigation for length, an investigation for mass, and an investigation for height. For each of these, I would need to write down a separate hypothesis. My hypothesis for length, just from the little thing that I've done earlier, my little observations, is this. I think that the longer, and I'm relating the variables, the longer the string, the length of string, the longer the length of string, the longer the time for one complete cycle. Okay, that's what I think. I think that length of string is going to make the time longer. We'll call that cycle the period or time. Period or time. So we're going to have to go and test that. What do we need to do? We need to make the mass the same. We need to make the mass of the bob and the height that we drop it from the same every time. Now, here's another thing. Because we want to be very careful, we want to do some measurements when we're doing this. So how are we going to measure? Let's talk about the measurements. We've got two factors. We've got a factor called length, the length of the string, and the time. For length, we're going to measure the length, and we can use a ruler, or we can use a meter rule, and we can measure it in units of centimeters, or the SI units are meters. But for the moment, it doesn't really matter which one we use. There are different instruments that we can measure length with. A ruler is one, but there are other instruments depending on how long something is. Time, remember, this is the thing that we're testing. Time, we're going to need to measure in seconds, and we're going to use a stopwatch here. So you could use centimeters and you can use a stopwatch. You're going to have to go about doing some measurements. How are you going to do it? Well, here's the important thing. We must measure as accurately as we can. What do we mean by accurately? Here's an illustration of two important words that scientists often would use. Let's think of a target, and the bullseye is the real answer, okay? So the bullseye right in the middle over there, that's what the real answer really is. Now, the more accurate we are, and I'm going to use our estimations in orange, the more accurate we are, the closer we will be to that center point. So over here, a reading over there and a reading over there, those readings are in the blue section. They're not going to be very accurate. Accuracy over there is going to be a bit better, but if we can get an accuracy right close to the middle, then we'd say that's really accurate. But one test won't give us perfect answer. What we need to be able to do is be able to recognize that these results or this experiment needs to be repeatable. And when something is repeatable and we get a whole collection of data that is not only accurate, close to the real thing, but we won't know what that real thing is, but that somebody else comes along and does the same experiment and gets the same results. Or if we do the same experiment over and over again, and we do it 3 or 4 times, not just once, but we get a collection of results. We find an average. Then what we're saying is it's not only repeatable, and it gives us consistent results. Then we say it's precise. So it's repeatable, and it gives us consistent answers. So it's consistent and repeatable. Then it will look something like this. Then that would not only be accurate, but also accurate and precise. So when we're doing any investigation, we must aim to be as close to the center. It must be as accurate as we can. But now, notice something here. We're going to use a stopwatch, and we're going to use here a ruler. A ruler and a stopwatch themselves have an error built into them. Because if you think about it, how do I know that as the pendulum starts that I've pushed the button exactly at the right time? How do I know that when the pendulum swings back to its original starting position, that it is exactly at that moment that I stop the stopwatch? Well, there's some ways that we can do, some things that we can do to overcome those inaccuracies. Human error, experimental error. We could use a really smart stopwatch. We could use something that is linked to technology that reads using a computer. But not everybody has that. Some people might just be relying on a watch that they're using, not even a stopwatch. That will be less accurate. But we can make sure that we can do it over and over again. Here's one way of improving the accuracy, and I want to show you this. If, first of all, instead of just holding up the pendulum, you secure the pendulum onto a stand. So you get a stand and you attach the pendulum. You could even attach it from the roof. And here's your pendulum, your string of pendulum. Okay, something like that. And now, instead of being unsure of where to start it, it's in a fixed position. And you can accurately make sure that you measure the height from the beginning as being the same every time you do it. The second thing that you can do is you can get your eye into line to make sure that your eye is at the right point when it swings backwards and forwards. I want to just show you another picture here and draw that diagram. I've drawn it from the side. I want to just get some more blank space here and draw the pendulum from the top. So here is your pendulum. Let's have it down there. There's the bob. And what we need to recognize is the pendulum is going to start from a position over here, say, and it's going to swing to that position, and then it's going to swing to that position, gets to that maximum position over there. So it goes from position A to position B to position C, and then back again. So the back again could be over here. Okay. Now, unfortunately, one of the things about this experiment, that what will happen with the pendulum is that there is some friction here. and the friction will mean that it doesn't quite get back to position A. So when we do this experiment and we want to improve the accuracy, we will always time the experiment when it passes B. And instead of timing it from A to C, B to C, back to B and back to A, this is what I suggest you do to make your experiment more accurate, because your eye can see the vertical position easier as well. You can get it into position and won't wobble around either. So as soon as it passes B, you push the stopwatch. It must go up to C, it comes back to B, it comes back to A, and it comes back to B. That's the same time, or the same amount of time. It's one cycle, but if we measure from B to C to A and back to B, that will give you a more accurate reading. And instead of just doing it for one swing, perhaps here's an idea. Instead of doing it just for one pass through like that, let's do it for 10 and measure what it takes for 10, because sometimes the timing for one might be very close. We might not be able to catch it on a stopwatch or on a watch. So I would suggest, if you're going to do this sort of experiment, then what you need to do is you need to do it for, say, 10 swings, and then do it 5 times. And in that way, you'll be able to get an average reading, and you'll see that your readings turn out to be very close to each other. Remember, the thing that you're going to then do is to change the variable, change the length, and see if length influences the period of the pendulum. Remember, the other variables, mass and the height that you drop it from, must remain the same. Then it will be a fair test. Okay, so I think that you've got an idea of how to conduct that sort of experiment. So why don't you just take a stretch, think about how you're going to do your experiments. We're going to go to a short break, and after this we're going to be looking at the relationship between variables. So I'll see you in a few minutes. Hi, welcome back. We've been looking at the skills that are important for doing science, the science toolkit, if you like. Now, what we've done so far is we've identified that the thing that makes science different is doing investigations. When we do investigations, we need to understand what the idea of a variable is. Variables all have values that we can measure or we can describe. What we've said in this last little section when we were looking at the experiment of a pendulum is that we need to make sure that all our experiments, all our investigations are fair tests, which means that we have one variable that is changing, which we know is the independent variable, and one outcome variable, which is the dependent variable. Now, if we want to describe the relationship between these variables, there's a way to do that. Sometimes we represent these relationships, we collect the data in a table, and then we can start to put those values which we are collecting, those values, those measurement values, into a graph. We can then describe the relationship based on what we see from the graph. So I'd like to do another idea. I want to show you something else. You don't have to learn this experiment. This is a technique of just describing relationships. So here's a spring. There are springs all around us. They do fascinating things, and they used to be really important. They're not as important now. But what we recognize is if we hold the edge of a spring, by applying a force, we can get the spring to increase its length. In other words, we can get a spring to stretch. Now, this one is quite a stiff spring, whereas other springs you might be more familiar with are quite easy to stretch. And they will, with a very little force, be able to give you a long length. Now, a very famous scientist, a man by the name, with the surname of Hooke, he did some experiments in terms of measuring the relationship between the force and the increased length of the spring. So I'm going to talk about the variables involved here of stretching a spring. And what we're recognizing here is that if we've got a spring, and we're going to stretch it, it's going to require a certain force. The thing that we are doing, we are changing. We are applying different amounts of force. So this is your independent variable. the distance above its increased length that it stretches, this is how much further it stretches. So when there was zero force, it's at its zero. The spring itself isn't 0 centimeters. The spring has a certain distance. This is the distance of its stretch. It's above its original length. So zero force, it's its original length. Now what we're doing is we're saying, let's increase the force. Let's have a 10 Newton force. What's the length? It's increased by 2 centimeters. And then we do 20. It's increased by 4 centimeters. And what we recognize is that as you go up and you increase the force, you increase the distance that it has stretched. So this is known as the dependent variable, because the amount of distance that it's increased is dependent on the size of the force that you've applied. But notice there's a pattern that exists here as well. That if we say take that as our original first one, 10 newtons, it stretches by 2 centimeters. If we double the force, that means we've gone to 20. Notice what's happened to the stretch. It's gone to 4. So in other words, we multiplied this by 2, doubled it, and this one doubled as well. They've not just increased. It didn't go up 2 and 3 and 5,5. It's gone up in a pattern. And so let's test if it happens again. So let's do it this way. Let's say, what happens if we double the distance here? Well, 4 times 2 will give us 8. Let's compare this value here to that value over there. And you can see, to go from 20 to 40, you've also multiplied by 2. There seems to be a pattern emerging, that as you double the one, you're doubling the other. They seem to be increasing, not just increasing randomly, but according to a pattern. Now, that is a special pattern. In this case, as you double one, or you multiply the one by a certain number, you multiply the other value by the same number. So the value of one variable multiplied by 2, you have to take the other value of that second variable and multiply it by 2. The pattern continues all the way through. And you can see that there's a consistency here. One way to test this is to say, well, hold on, let's see if we ask a question about the relationship in this way. Instead of doing a multiplication, let's take a look at the ratio of distance over force. So I'm going to put in another line over here, and I'm going to say, let's take the distance, and I'm going to take the force over there. And if I take distance over force, then I'm going to say this is 2 over 10, which is going to be 0,2. And 4 divided by 20 is 0,2. And 6 divided by 30, 0,2. There is a constant ratio between the distance and the force. They seem to be consistent all the time. So if we take 10 over 50, we'd get 0,2. Now, that has a special relationship. And you can do it algebraically like that. Or, as I said earlier, we can plot a graph. I'm going to just sketch a graph here because I want to put in the important parts of drawing a graph for you. So when you draw a graph, you usually will use graph paper or squared paper, blocked paper. You'll need to draw in your axes. Make sure that you've got your axes. That one doesn't look very straight, so let me just redraw it. Put in the axis over here, the horizontal axis. And here's the important thing now. We're going to have to decide, where does each of these variables apply? Well, as a rule, we put the independent variable, the one we change, force, on the horizontal axis. Force in newtons. And this is the distance, the stretch, the extra distance. And we say it's in centimeters. I suppose we could change it to meters if we wanted to, but I'm not going to worry about that just yet because we'll need to add some detail here. Now, when we've got a graph like this or set of axes, we're going to need to determine a scale. And it's really important that you take note of the values and that you plot the values on your graph paper according to even spacing, according to a scale, so that they all fit in. You don't want your graph to be too small so you can't see, and you don't want it to be stretched out. It must be evenly spaced. So let's have a look at the force values. We went up from 0 to 50 and we were evenly spaced. Now I'm not going to be able to do that because I'm just going to put 0 and 50 over there, and I'm just going to do it freehand. 10, 20, 30, 40, and I'm going to move that 50 and bring it a little bit closer and say that one can be the 50 over there. Now I've tried to do it as evenly as we can, and then over here we're going to go to 0 to 10. So we're going to say don't skip out any numbers, make that 10 at the beginning, make that 1, make that 2, make the middle there 5, that's going to be 4. You don't want to squash things up, that's why they must be even. So this one will be 6 over here, 7, 8, 9, and so on. Now, once you've got your scale all sorted out and you've set it up so that these spacings are even and they're all nicely set out, you can use a ruler to do that. You can then go about plotting your points. Now notice this one is 0, 0. It's a very, very important point. When we have a special relationship that I'm going to describe like this one, it will always pass through the 0, 0 point. Now for 10 newtons, we got a stretch of 2 centimeters. So when you go to 10 newtons, you go up over here and you plot a point over there in line with the 2. Now, you can plot points, and that's a maths thing. I'm not going to carry on doing that. I'm going to plot one more point on this graph, and then I'm going to draw a line that will fit through the points as best as they can. In this case, it will be a particular shape, which I'm sure you can all already see. 10, 10 over there, and 50 over there is going to give me a point somewhere over there. And I'm going to use a line to join these points. In most cases, you'll be able to use a ruler to draw through the majority of the points. This is known as a best fit line. In this case, if we now go and see, you'll see that roughly 20, 30, 40 will be over here, and so on. They will form a straight line. A straight line passing through the origin will give you this sort of relationship. The relationship has a special name. We say that these variables are directly, we say that the special name for this relationship is directly proportional. Now, in maths terms, what we're going to do is we're going to say, let's put D for distance and F for force, and we're going to say distance is directly proportional to force. Now, there is another way of representing that. Instead of putting that funny sign, which means directly proportional, we can recognize that for this particular spring, we can make a constant here. The distance over force relationship gives us a constant. You should see from the graph, the gradient of this line here, the gradient is the distance over force, and because it's a straight line, it is a constant. So what we can do is, instead of writing it like that, we can say, well, distance, instead of it with the proportional sign in, we can say distance is equal to a constant times the force. So in that way, we've got a way of describing. We've developed an equation to describe the relationship. What Hooke did, he actually said force is equal to 1 over that constant times distance. So You can write it around in the other way, just making force the subject of the formula divided by 1 over k. It's still a constant. This is known as the spring constant. You don't have to know that, but I just want you to recognize you come up across signs constants in many equations, and that's what it's telling us. That when two variables are directly proportional, that we can say this one equals that one times a constant. And it's because we've got this particular type of relationship, directly proportional. Now there's a second type of relationship that's not directly proportional that I want to deal with now. So let's move on to that quickly. And here we go. Electric circuit, resistance and current. Notice here there is a trend. And we're going to say we're controlling the resistance. So this is the independent, and that's your dependent. We're going to control the resistance. What's happening to the resistance? The resistance is increasing. What's happening to the current? Oh, notice here it's decreasing. But that's not a very strong relationship, as the one increases, the other one decreases. Although it's true. But what we recognize here is that if I double this one, so I multiply this one by 2. 2 times 2 is 4. What happens to this one? 12 to 6. I didn't multiply by 2, but I multiplied by a half. So this one is a reciprocal. These are reciprocals. The one is 2 over 1, and that's one's 1 over 2. They're inverses of each other. So the relationship here, let's test it. Let's try another one. 6 goes to 12. That's also multiplied by 2. Let's see what happens. From 4 to 2, multiply by half. Oh, looks like we've got the relationship. This isn't a directly proportional relationship, but it's known as inversely proportional. Now, when you plot this graph, you don't get a straight line, because as the one increases, the other's decreasing. We're going to plot the independent variable and the dependent variable in the same way, but we won't get a straight line. What I also need you to recognize is that if we take 2 and 12 and 4 and 6 and 6 and 4 and 8 and 3 and 12 and 2 and 16 and 1,5, we start to think about, well, what happens if we put them over each other? Doesn't seem that the number is getting the same. But what happens if we multiply them together? 2 times 12 is, well, you've got it, 24. What about 16 times 1.5? Well, guess what? It's also 24. And 2 times 12 over there is 24. It looks like if we multiply resistance times current, we're going to get a constant. These two, resistance and current, then, are inversely proportional. And we'd say R is not directly proportional, but is directly proportional to 1 over I. So that's how we represent inversely proportional. We do the 1 over because of the inverse idea. Now the graph, just quickly, and I'm not going to plot all the points, I just want you to see what this graph will look like. If I put resistance and current, and I put current in amps and resistance in ohms, then the graph, starting with a large resistance, will have a low current. It will look something like that, a curve. And that's not very helpful. So what scientists do, what physicists do, is they say, well, let's do a 1 over relationship. And that's exactly what they do. They say, let's, like I've done over here, let's do 1 over I. So what we'll find is we do R and 1 over I, and now you'll get a straight line. So what we're saying is R is directly proportional to 1 over I. Now, you can go and try that. Do a plot. Practice your graphing. It's one of the important skills you're going to need. But I think it's really important that you know and you understand those two relationships when we're dealing with investigations. Learn to identify directly proportional and inversely proportional relationships. Okay, now we're moving on. And the next thing we're going to go to is the idea of some math skills that are really important. We're just going to conclude today's lesson by looking at some math skills. Here's a question for you to think about. Is there a difference between 6 centimeters and 6,0 centimeters? Think about it carefully. I think you need a short break. While you're thinking about it, have a break, have a stretch, have a glass of water. I'll see you in a bit. Welcome back. What if you've had some ideas about the difference between 6 centimeters and 6,0 centimeters? Well, yes, there is a difference, and it's a very important difference. When we give the answer as 6 centimeters, we're actually saying we think it's somewhere between, it's not 5 centimeters and it's not 7 centimeters, it's somewhere between those two. Our instrument that we're using isn't terribly accurate. So it's either it's about 6 centimeters. The margin of error is 1 centimeter on either side. But this tells us, listen guys, we actually know it's somewhere between 5,9 centimeters and 6,1 centimeters. We've got a much more accurate measurement here. This one we're uncertain. There's a bigger uncertainty. It is less accurate. So what I'm trying to do this for is to say to you that when you've got experiments, we need to be aware that sometimes a watch isn't very accurate. A computer timer is far more accurate. And so that's why our decimal places, particularly after the 0, are very important. It tells us how accurate our instruments are. If our instruments are not accurate, we can't be certain. And that's telling us something that sometimes a lot of learners forget. And brings us to an important point. Whatever we do, we need to be careful about using the answers that we do get. In our experiments, we need to think about this idea of uncertainty. We say that this one is, because it's got a 0 there, it is more accurate. So we must be careful when rounding off. If we are given the general rule, in most exam questions, they say to you, you must give your answer to 2 decimal places. To 2 decimal places. 2 decimal places, and how do we round off? So if I got an answer of 0,594, if I leave it 4, 5, 6, 7, that's telling me I've got a very accurate measurement. I haven't got that accurate measurement. I must round it off to 2 decimal places. What do I do? How do I do it? Here we go. We look at our 3rd decimal place. That, in this case, it's a 4. We say to it, if it's less than 5, then we can just ignore all of those values. If it was 5 or bigger than 5, then we'd have to change this value and increase it by 1. So be very clear about how you round off. The next thing that we've got to do when we're dealing with a calculator is make sure that we understand the idea of scientific notation. And I'm just going to fly through this very quickly. Sometimes we deal with very big numbers, like the speed of a light is 3 times 10 to the 8. Now, I don't want to write down all the zeros. Or we might deal with a wavelength of light of 550, 5,5 times 10 to the minus 7 meters. This is meters per second. This is very big. You don't want to be writing all the numbers, all the zeros. So that's why we put an exponent in there. Now, the calculator helps us do that. You must make sure that when you use your calculator, that you're very familiar with it. Right, we write 3 times 10 to the minus 10, the exponent button. Now we want to write the 8 in, and we put the 8 over there. That's 3 times 10 to the 8. So that would be the speed of light. Now, what about doing it for a smaller value? So if we were to do it to our other value, 5,5, the exponent, minus 7, and you've logged it into the calculator. Then you can multiply and divide just as you would normally do it. So please be very familiar with your calculator and using scientific notation. It's an important math skill. Now, another important math skill is making sure you understand the idea of the SI units. Very easy system of units to use, and it's something that we're going to use the scientific notation with as well. The SI unit stands for the System International. It's based in Paris. All the scientists got together and they decided on some units, some standard units, and they've defined those very carefully. There are 7 standard units, and you'll find them mentioned here. The SI base units are units of length is a meter, mass is kilogram, time, the base unit for time is seconds, and the symbol is S. Electric current is ampere, and the symbol is A. Temperature is Kelvin, and K. The amount of substance is measured in mole, and luminous intensity, how bright a light is in candela, and the symbol is CD. Now, we will be dealing with the 6 of those over the course of your 3 years of doing physical science, but some of these units are either too big or too small. So we're going to have to change them. And so that's why in the SI units we have prefixes that tell us that they're either much bigger than the standard or smaller than the standard. And here are the ones that you'll need to know. So giga is G, so it would go in front of the unit, and that's 10 to the 9. Then mega is 10 to the 6. Kilo is 10 to the 3. Important thing to notice here is that kilogram is the base unit. So even though it's got kilo is times 10 to the 3, in kilogram that's already there. So it works a little bit differently with mass. Milli is times 10 to the minus 3, and micro is 10 to the minus 6. Nano is times 10 to the minus 9, and pico is times 10 to the minus 12. You'll notice that each of these is 1,000 difference, so we'll be able to work through those. Let's have some practice at looking at some examples of converting units. And here we go. If I've given 550 gigawatts, how many watts is that? Watts is a unit of power. This is how I do it. I say 550 times, now giga was 10 to the 9. Okay, so I'm going to write that onto the calculator. Let's just clear what we've got there. I've got 550 exponent 9. So that's the G stands for times 10 to the 9. And if I put that as an equal, it will give me 5,5 times 10 to the 11, because it's included the 2 decimal places there. So I'm going to write the answer, final answer, as 5,5 times 10 to the 11 watts. I've converted from gigawatts to watts. What about going smaller? 350 amps. So 350 milliamps, I'm going to replace the milli by 10 to the 3. Back to our table just to check on the suffixes, the prefixes, and you'll see that milli is times 10 to the minus 3. So that's where I got it from. I'm going to say 350 times 10 to the minus 3 amperes. Now I could leave it like that in a calculation, or I could give the whole answer, do it on the calculator, and get the answer 350 exponent minus 3 equals, and it's given to me as a fraction. On the calculator I can convert it to the whole number, 0.35 amps. So put it into whole numbers. When they're less than 1,000, you can write the answer like that. It's no longer in scientific notation. My rule is if it's got 2 decimal places, that's fine. If it's 3 decimal places, rather put it into scientific notation. Well, what about 300 nanometers? Well, I think you can do this one almost in your head. Well, we're going to say 300 nano is times 10 to the minus 9, and we can now look and do it in our heads. Minus 9, but that's it's going to be, we want it to be a single digit, 3,0, 0, strictly speaking. What have we done? We've divided by 100 to get there. So we must multiply this by 100. So I'm going to multiply that by 100. 100 is times 10 to the 10 to the 2. So that's going to be minus 7 meters. So there we are. We've done it in our head. Let's make sure that you've got that sorted out. Try and practice it. Do it in your head. Do it on the calculator. Compare your answer. Let's go to the last one of these conversions. We've got 2,5 meganewtons. What is that? 2,5 mega. Check the prefix. Make sure you've got it right. Mega is times 10 to the 6. Kilo, mega, giga. So we go back over here. We're going to say times 10 to the 6 Newton. Okay. What about this example? What is 60 kilometers an hour in SI units? Think about it. A little bit different to the ones that we've done before. Now, the way that I like to do this when I'm first doing this, I say, well, that's 60 kilometers in 1 hour. And I must change 60 kilometers into meters. So kilo means that it's times 10 to the 3 meters. And hours, well, I want to change from hours to seconds. So there's 60 minutes in 1 hour and 60 seconds in a minute. So it's 60 times 60. And if I do that, what you're going to see is that you're going to cancel this one out. Let's just do it on the calculator so we can see. We're going to go 60 exponent 3 divided by, and I'm going to put it in brackets so you can see it, 60 times 60. And there we go. 16,6666 recurring meters per second. Remember the rule, 2 decimal places. So what we're going to do is we're going to write that as equal to 16,67 meters per second. Now, some of you are saying, but hold on, that was a lot of work. What did we actually do? Is there another way of doing it? Well, fortunately, there is. If we multiply by 1,000 and divide by 3,600, well, then, in fact, what you can do is you can take your answer of 60 and divide by 3,6. And if you do that, you get the same answer, 16,66. So there are 2 ways. There's the long way, or you can say, and you need to, if they ask you to explain it and to show your working, you need to do it this way. But if you're doing it just shorthand, then you're going to say kilometers per hour to meters per second. All that you've got to do is divide by 3,6, and you will get the answer of 16,67 meters per second. If you're going the other way, what do you think you're going to do? Remember, meters per second will be smaller than kilometers per hour. So what are we going to do? If we go from meters per second to kilometers per hour, multiply by 3,6, and here that's exactly what we've got to do. In this case, we're going to say 20 meters per second, and we multiply by 3,6, and that will give us the answer in kilometers per hour. Here's the calculator, 20 multiplied by 3,6, and that will give us 72 kilometers per hour. 72 kilometers per hour. Okay. Let's look at this one. We're asked to convert 30 centimeters cubed to meters, 30 centimeters squared to meters squared. Now, meters squared is an SI unit for area. You need to be able to compare and convert from centimeters squared to meters squared when you're doing pressure calculations. And those sometimes come up. So this is one area where you need to understand about area. The way that I think about it is as follows. If I've got a 1 centimeter by 1 centimeter block, that will be 1 centimeter squared. If I've got a 1 meter block by 1 meter, well, that's also can be written as 100 centimeters by 100 centimeters, which means that 1 meter squared is equal to 100 times 100, which is 10 to the 4 centimeters squared. That's 10,000. So when we're converting, we need to recognize that we take the centimeters squared to meters squared, going from the smaller unit to the bigger unit, you're going to divide. So we say, in this case, we're going to say 30 centimeters squared divided by that factor. We're going to divide this one by 10,000, and it will give us into meters by 10 to the 4, and we will then be able to give an answer. So let's do it on the calculator. 30 divided by 1 exponent 4 gives me an answer of 3 times 10 to the minus 3. And that is your answer in meters squared. 3 times 10 to the minus 3. Check it. 3 times 10 to the minus 3. Yes, we've got it. 3 times 10 to the minus 3 meters squared. A meter squared is really quite a big unit. Doesn't come up very often, but I think it's important that you do know it. The next one is also important. Right, 250 centimeters cubed. Now, volume measurements. Interestingly enough, 250 centimeters cubed is equal to 250 milliliters. And that's also equal to, we know that 1 liter is 1,000 centimeters cubed. But that's equal to 1 decimeter cubed. So when we're talking about milliliters, centimeters cubed, and decimeters cubed, they're related to each other, and it's really important that you know what the difference is. So it's easier if you can think about it, converting milliliters or centimeters cubed to milliliters first of all. Then you can see, well, let's convert it to liters. Well, I've just said 1,000, we know, milli is 10 to the 3. So it's easy to recognize that this is 0.25 liters. It's a quarter of a liter, which means that it's 0.25 decimeters cubed. And in some chemistry calculations, we use decimeters cubed as a standard unit. Okay, now there's one last thing other than converting units that I want to take you through. And I'm going to do this very quickly. And that is working with equations. You need to make sure that when you're doing some science problems, that you're able to work with equations really well. Now, I'm going to show you very briefly just one quick calculation and then give you some tips for answering science-based problems. So here we go. Here's one. The density of a substance is the ratio of mass to volume. You might have come across that in grade 9 or even grade 8. So we use the symbol, this funny symbol here is called rho. Mass is m and v is volume. It asks us simply to calculate the mass of a block of aluminium. Tells us the mass of a block of aluminium. That's what we've got to find. We've got to find mass. It's not given. We're told the volume is 50 centimeters cubed, and we're told that the density is 2,7. The density is 2,70 grams per centimeter cubed. So we want to find mass. We've been given the equation to use. So how are we going to do it? Well, this is my suggestion. You can get all fancy. My suggestion is that you just write down the given equation and you substitute the values in. In some cases, you're going to need to change units to SI units, but in this case, I don't think that's an issue. We can work it out in grams and then convert to kilograms. That will be easier. So we're going to write down 2,70. We're going to say is equal to the mass divided by the volume, which is 50 centimeters. And that means we can now change and get mass on its own. The reason that we substitute and don't change the formula is that you would get marks for identifying and doing the correct substitution. Then if you manipulate, now we're going to have to manipulate. How are we going to get rid of that 50? We multiply both sides by 50. We can say, therefore, mass is equal to 2,70 multiplied by 50. If I multiplied by 50 and I switched around, so I've got mass on its own, what I did to the one side, I did to the other. The 50 cancelled out with that 50, and that one's got multiplied by 50. Let's use the calculator, and we'll be able to work out the mass. So we're going to say 2.7 multiplied by 50 gives us 135 grams. So check the units. The reason that it's grams, 135 grams, is that this was grams and that was centimeters cubed. Centimeters cubed times per centimeters cubed, those are going to cancel, and I'm left with grams. If I were to write as SI units, I've got to change it to 0,1. Now, 2 decimal places, 14 kilograms. Okay, and there we go. Because 5 is at the halfway point, we round up. It's the 3rd decimal place, and we've put it into place. Now, lastly, here are some tips for you. Whenever you are doing a science problem, try to illustrate it with what I've just done. Here are 6 points that I want you to remember and you must work through. When you get a science problem, that's usually like a word problem. Read it carefully, and then, if necessary, draw a little diagram. I like to draw sketches. Put the things down, but at least write down all the given information and identify what you need to find. Then select the correct equation. Write down the equation that has been given to you. You're usually given a data sheet, or the equation is somewhere given to you on the paper, or you've learnt about it in your textbook. The next thing is to make sure that the values you've got, remember the difference between variables and values, the values you've got have units that are SI units. Convert to SI units. So that's the important thing. And then substitute those values in, and then do a little bit of a manipulation and solve for your unknown variable. Now, those tips will help you solve the majority of science problems that you may have in your tests or exams. We're going to be doing a lot of those as we do the end of chapter exercises from your science textbook, and so I hope you will join us again as we continue to explore this world of science. And I hope these science tools that we've gone through today will stand you in good stead to not only make you a good student of physical science, but inspire you to become a scientist yourself. Bye for now. Yeah.